Hi guys, welcome back to engineeringtalks.com. In the previous video, we saw the method of finding out the inverse Laplace transforms of the functions using partial fractions. Today, we'll go through the topics Laplace transforms of derivatives and Laplace transforms of integrals. And we'll solve problems on both the topics. So happy learning and don't forget to like, share, subscribe and press the bell icon. First, let's go through the Laplace transforms of derivatives. For a function to be differentiable, it has to be continuous first. So, if a function f of t is continuous for all values of t greater than or equal to 0 and is of exponential order, that is, it satisfies the inequality mod f of t less than or equal to m e raised to ct, where m and c are constants. I have explained this in the first video about Laplace transforms, so please watch that video first. And if such a function has derivatives such as f dash of t, f double dash of t, f triple dash of t up to fn of t, which are piecewise continuous. Why piecewise continuous? This is a mandatory condition for the Laplace transforms to exist. Only if the function is piecewise continuous, we can take the Laplace transform of that particular function. So these derivatives must be piecewise continuous on every interval in the range t greater than or equal to 0. Then we can say that Laplace transforms exist. So let's see how we can take the Laplace transforms of the derivatives. Laplace of f dash of t is given by s Laplace of f of t minus f of 0, which is equal to s f of s minus f of 0, because Laplace of f of t is f of s. Laplace of f double dash of t is equal to s square Laplace of f of t minus s f of 0 minus f dash of 0, which is equal to s square f of s minus s f of 0 minus f dash of 0. Similarly, Laplace of f triple dash of t is equal to s cube Laplace of f of t minus s square f of 0 minus s f dash of 0 minus f double dash of 0, which is equal to s cube f of s minus s square f of 0 minus s f dash of 0 minus f double dash of 0. So, in general, we can write it as Laplace of f raised to nt is equal to s raised to n f of s minus s raised to n minus 1 f of 0 minus s raised to n minus 2 f dash of 0 minus up to minus f raised to n minus 1 0. Now let's see how we can get the Laplace transform of the function t cube using this expansion. So we have f of t is equal to t cube. So f of 0 will be 0 cube, which is 0. And f dash of t will be, that is df by dt will be 3t square. So f dash of 0 will be 0. Similarly, f double dash of t will be 60 and f double dash of 0 will be 0, and f triple dash of t, that is d cube t by dt cube, will be equal to 6. So we have the expansion for Laplace of f triple dash of t. Laplace of f triple dash of t is equal to s cube f of s minus s square f of 0 minus s f dash of 0 minus f double dash of 0. We already know that f triple dash of t is 6. So Laplace of f triple dash of t will be Laplace of 6, right? So 6 into Laplace of 1 will be 6 by s, because Laplace of 1 is 1 by s. Let's substitute all these values. We'll get 6 by s is equal to s cube f of s minus s square into f of 0 is 0 minus s into f dash of 0, f dash of 0 is 0 minus f double dash of 0, f double dash of 0 is also 0. So 6 by s is equal to s cube f of s. Therefore, f of s is equal to 6 by s into s cube, that is 6 by s raised to 4. Let's solve an initial value problem. Here we have to find out the solution of the differential equation given by d square y by dt square plus 4 dy by dt plus 4y is equal to 0, or y double dash plus 4y dash plus 4y is equal to 0 with the initial values y of 0 is equal to y dash of 0 is equal to 1. Let's take the Laplace transform. Laplace of d square y by dt square plus 4 dy by dt plus 4y is equal to Laplace of 0, right? Now let's split these terms using the linearity property and write it as Laplace of d square y by dt square plus 4 Laplace of dy by dt plus 4 Laplace of y is equal to 0. Why 0? Because Laplace of 0 is 0. Now let's expand. S square y of s minus sy of 0 minus y dash of 0 plus 4 into sy of s minus y of 0 plus 4 into y of s is equal to 0. Now we will bring the coefficients of y of s together and write it as s square plus 4s plus 4 into y of s minus sy of 0 minus y dash of 0 minus 4 into y of 0 is equal to 0. We will bring these three terms to the RHS. So it becomes s square plus 4s plus 4 into y of s is equal to s into y of 0 plus y dash of 0 plus 4 into y of 0. Now we know that y of 0 is equal to y dash of 0 is equal to 1. So s plus y plus 1 is equal to s plus 5. Therefore, y of s is equal to s plus 5 by s square plus 4s plus 4. That is, we can bring this 1 by s square plus 4s plus 4 term to the RHS in order to obtain the value of y of s. And this function 1 by s square plus 4s plus 4 is known as the transfer function. We'll deal with this topic in a separate video. Now we want the solution in t space. This is in s space. So the solution has to be in t space. So in order to obtain y of t, we have to take the Laplace inverse of this function. So before taking the Laplace inverse of this function, we have to split it into partial fractions. So s plus 5 by s square plus 4s plus 4 is equal to s plus 5 by s plus 2 the whole square, right? Because s plus 2 the whole square is s square plus 4s plus 4. So we can write it as s plus 2 the whole square. Now we have a repeating linear term in the denominator. So when we have a repeating linear term in the denominator, the partial fraction takes the form a by s plus 2 plus b by s plus 2 the whole square. So s plus 5 is equal to a into s plus 2 plus b. That is, we have just made the denominators equal and equal to s plus 2 the whole square. So we just cross multiplied and made the denominator equal. So s plus 5 is equal to as plus 2a plus b. Now let's equate the constants. We have this equation. Now when we equate the constants, we'll get it as 5 equal to 2a plus b. And let's equate the coefficients of s now. On LHS we have one s term and on RHS we have one as term. So when we equate the coefficients of s, we'll get 1 equal to a. So we got the value of a. Now let's substitute this value of a in equation 1 in order to obtain the value of b. Therefore 5 is equal to 2 plus b and b is equal to 3. Now we'll substitute these values in this equation. Therefore we'll get y of s is equal to 5s plus 5 by s square plus 4s plus 4, which is equal to 1 by s plus 2 plus 3 by s plus 2 the whole square. Now taking the inverse Laplace transform, we'll get Laplace inverse of y of s is equal to y of t, which is equal to Laplace inverse of 1 by s plus 2 plus 3 into Laplace inverse of 1 by s plus 2 the whole square. So on taking the inverse Laplace transform of the function, we'll get these two terms. So Laplace inverse of 1 by s plus 2 is e raised to minus 2t, and Laplace inverse of 1 by s plus 2 the whole square is e raised to minus 2t Laplace inverse of 1 by s square. See here in the denominator we have s plus 2 in the place of s. So this s plus 2 is due to e raised to minus 2t. So when we take this e raised to minus 2t outside, we'll have only 1 by s square. Therefore, e raised to minus 2t plus 3 e raised to minus 2t into Laplace inverse of 1 by s square. Laplace inverse of 1 by s square is t. Therefore, the final answer is e raised to minus 2t plus 3t e raised to minus 2t, which is equal to e raised to minus 2t into 1 plus 3t. Now, Laplace transforms of integrals. If a function f of t is piecewise continuous and satisfies the inequality mod f of t less than or equal to m e raised to ct for all values of t greater than or equal to 0, then we have Laplace of integral 0 to t f of u du is equal to 1 by s f of s. So, using this property, let's find the Laplace transform of integral 0 to t sin t dt. So, we know that Laplace of integral 0 to t f of u du or Laplace of integral 0 to t f of t dt is given by 1 by s f of s, right? So, here f of u or f of t is given by sin t. So, first we have to find out the Laplace transform of sin t. So, f of s is Laplace of sin t, which is equal to 1 by s square plus 1. Therefore, Laplace of integral 0 to t sin t dt is given by 1 by s f of s. So, 1 by s into 1 by s square plus 1. That is the Laplace transform of sin t. Therefore, Laplace of integral 0 to t sin t dt is equal to 1 by s into s square plus 1. Laplace transform of a function is given as 1 by s square into s square plus a square. Now let's see how we can find the value of f of t using the property Laplace of integral 0 to t f of u du is equal to 1 by s f of s. So we have Laplace of f of t is equal to 1 by s square into s square plus a square. And we already know that Laplace of integral 0 to t f of u du is equal to 1 by s f of s. So integral 0 to t f of u du is equal to Laplace inverse of 1 by s f of s, right? Or Laplace inverse of 1 by f of s is equal to integral 0 to t f of u du or integral 0 to t f of t dt. Now, we have the function Laplace of t is equal to 1 by s square into s square plus a square. Now, in order to find out the f of t value, we have to take the Laplace inverse of this function, that is 1 by s square into s square plus a square. So, first for time being, let's consider 1 by s into s square plus a square as the function. So, Laplace inverse of 1 by s into s square plus a square will be equal to integral 0 to t f of u du, right? This is of the form 1 by s f of s. That is, this is of the form 1 by s f of s. So, Laplace inverse of 1 by s f of s is equal to integral 0 to t f of u du or integral 0 to t f of t dt. So, first we have to find out the f of t of this function, that is 1 by s square plus a square. For that, we have to find the Laplace inverse of 1 by s square plus a square, which is equal to 1 by a sin at. Because Laplace of sin at is a by s square plus a square. So, Laplace inverse of a by s square plus a square is sin at, or Laplace inverse of 1 by s square plus a square is 1 by a sin at. Therefore, Laplace inverse of 1 by s f of s, that is Laplace inverse of 1 by s into 1 by s square plus a square is equal to integral 0 to t f of t dt. Here f of t is 1 by a sin at, which is the Laplace inverse of 1 by s square plus a square, which is equal to integral 0 to t 1 by a sin au du. Therefore, integral 0 to t 1 by a sin au du is equal to 1 by a into minus cos au by a, that is the integral of sin au within the limits 0 to t. Let's apply the limits. So, 1 by a square into minus cos at minus of minus cos 0. Cos 0 is 1. So, minus of minus 1. Therefore, 1 by a square into 1 by a square into 1 minus cos at. Now, let's consider Laplace inverse of 1 by s square into 1 by s square into a square. Before we considered 1 by s into 1 by s square plus a square. Now, we have the function 1 by s square into a square plus a square. So, let's rewrite it as Laplace inverse of 1 by s into 1 by s into s square plus a square. Now we have this in the form Laplace inverse of 1 by s into f of s, which will be equal to integral 0 to t f of u du. Here f of s is 1 by s into s square plus a square. So here we should have that f of t value. In order to get the f of t value, we have to take the Laplace inverse of 1 by s into s square plus a square. So Laplace inverse of 1 by s into s square plus a square is equal to integral 0 to t 1 by a sin au du, which is equal to 1 by a square into 1 minus cos at. We already got it here. So let's substitute that. So Laplace inverse of 1 by s into f of s, that is Laplace inverse of 1 by s into s square plus a square is equal to integral 0 to t f of t or f of u du, which is equal to integral 0 to t 1 by a square into 1 minus cos au du, which is equal to 1 by a square into u minus sin au by a within the limits 0 to t. Let's apply the limits. So we'll get it as 1 by a square into t minus sin at by a. Therefore, f of t is equal to 1 by a square into t minus sin at by a. I hope it's clear. Please do like, share and subscribe the channel. Thank you.